Hello everyone and welcome into yet another live stream. Let me just check the day, change the day to 71 and color white because it's no everyday day. And welcome to yet another live stream. Today we are going to science. It's Science Tuesday. Yeah, obviously we'll still be working on our lovely paper. Google Docs. I know you can't see anything, but just give me a second. Not a scientific paper. There we go. And there we go. That's it. Yeah, there are two things that we basically should do. Two of them. One thing that I have to do in order to fix my previous mistake, and one as a new thing, as something new to to do. So let me first. I'm sorry for something streaming it. I mean closing it, but I just need to do some stuff in order to set up the stream correctly. All right, there we go. This should be all right now. Okay, some music. What a lovely idea. Copyright free electro swing by Odd Chap. Oh, that's wonderful. All right, great. So now, what's the first thing that I should fix? The first thing is the fact that last time we took a shortcut. By we took a shortcut, I mean I just straight up missed one thing. The omegas. When it comes to the omegas, there's a problem with them. We don't actually have a proof that they contain every single number. There is only one more wrinkle to iron here, and it is the fact that so far we have not proven that omegas. Let me just copy one of this. Omegas. Omega that there is an omega n that contains any number, let's see, any number q for a given n. And that's a problem. That's a rather big problem, rather large problem. But I actually have no idea if it's provable, but we'll try. We will certainly try. I feel like the music might be a bit too loud. We will certainly try. I have one idea on how to do it. Because basically there's a couple of things that we need to prove in order to prove that we should first show that omegas, that a set of that omegas contain all the numbers, and in order now how are we going to do that? Let's start small by proving that for any omega n there exists an omega n plus 1 which has more numbers. Yeah, surprisingly, yeah, we still haven't proven that, by the way. There is a possibility, because in theory there's a possibility that it would just flatline, that it would just, stop. So, how are we going to prove that? Well, with help from the old friend, really old friend, half function. Yeah, we introduced the half function on the first page, if I'm not mistaken. Maybe second, yeah. Half function, there it is. The half function. No, that's the half, and half function is over here. That's the half function, and we haven't used it since, but right now it could really come in handy. Why? Well, it's because starting with more numbers. Which contains more numbers? Well, it sounds more right, okay. Just more numbers. This could be false if there is an omega n, which is equal to omega n plus 1. I know that doesn't take n, which is equal to omega n plus 1, which would basically mean that there would be a point which you would be operating on a set of numbers so large that no hyper operation would increase its size. So first, let's prove it by contradiction, I guess. I mean, it's the simplest way to prove stuff, in my opinion. Would be easy. So let's assume that there are two numbers in some omega n between which you cannot create any other number. So some numbers, let's call them q, p and q, in some omega n, create any number with any hyper operation. Cannot create any other number r. No, that's right. Yeah, we should do something like cannot create any other number. I just feels like delta of any hyper operation, so that p would be smaller than delta, which would be smaller than q. Yeah. Yes. Now, very interesting thing to note is that those numbers do not have to be next to each other. There could be numbers that exist in between them, but the point is that they cannot be reached with hyper operations. Let me just... okay. There could be numbers in between q and p, but they could not be reached with a hyper operation. With any hyper operation. That would mean... it would mean that it would mean that increasing the n would not create any new numbers in between them. Yeah. Now it's time to oh, I love this. Okay, great. So now what we have to do is we have to prove that if those numbers will exist, there will be some kind of contradiction based on that. So we have our p, which is smaller than delta, which is smaller than q, right? And now what we basically say is that delta is unreachable to any combination. Because here's the thing, if we prove that, if we get a contradiction, that's really interesting, because based on that we could prove that deltas contain every single number. If we don't get a contradiction though, I mean, if we don't get a contradiction, which means if this would be true, then that's also interesting, because that means there will be sets of numbers, which is... yeah, I'll mention later. Okay. So then that was smaller than p. Now, it's time for a half. Half operation is interesting. It is very interesting because you see half operation when half of one, so like when of n is operated on x with up arrow and up arrow like this, when this is operating on at h n of x, we get x. That's what halves are. That's what half functions are. Which means that in this case, so n would be the last hyperoperation. Yeah, so in this case, omega n would be the smallest omega containing the q. That's also very interesting. That's important because then that also gives us an n, and that means n is actually a part of this, which means that n of p, right, operated by n p. So this n is only unlocked in this omega. That's why this omega works at all. So now what we have to do is we have to just prove somehow that we can get numbers in between. How can we? Well, so glad you asked. Because there's a possibility that would be a fixed point, right? So operating on higher operations would give us nothing. Okay, that's a good question. I'm pretty certain we had the definition of half function, right? We did define it somehow. Do we not? Wasn't half... It's just inverse? Oh, it's just... Oh, n plus 1, 2. Alright, so... half function then. No, sorry. As a warm-up, let's define the half function correct with half function x equal to x down arrow and down arrow n plus 1, very important, 2. That's a very important thing. That's the half function then. So yeah, that's the half function. That's also very interesting because wait, if we expand that, then what we get is basically p down arrow n plus 1 down arrow 2. I just feel like half functions would be important in this case. We could expand that obviously, but I'll keep it as a half function for now. Oh, what about the half function of delta? I mean, half function of delta has to exist. Yeah, half function of delta has to exist in comparison, like, not for any. Yeah, it has to exist for this hyperoperation too. But it would not be in the set then. The interesting thing is that inequalities stay the same, which basically means that half function of p would be smaller than half function of delta, which would be smaller than half function of q. That would still be the same. Because right now what I'm trying to do is I'm trying to prove that this number is reachable with some hyperoperations. Well, of course it is. Wait, I'm an idiot. Of course it is. Of course it is. Wait. Oh, that's so obvious. It so obviously is. We can just write an equation for some delta. Oh, that's so obvious. Oh, that's so disappointing. Yes, because yeah, equation would look like this. Basically, you'd have p q, right? P minus q, which would give us the distance in between them, and then that just halved in comparison to operation n. Because, well, in that case we don't even need, wait, in that case we don't actually, we can just half it with division. Wait, something is off. And then add p again. Something is off, we can just half it with division. I don't like that idea. Divided by 2, up. P. That gives us delta. So P smaller than this is smaller than Q. That would give us some kind of delta. That would satisfy this. That, I mean, I guess, but it's, why is it not in relation to any hyperoperation? That's so bizarre. Wait, what? Wait, also wouldn't that mean that you can reach any number? No, wait, oh, because that's a complex equation. Oh, that's a complex equation, okay. Because that's a complex equation, that's why, obviously, my goodness, I'm such an idiot. That's a complex equation. As down arrows and up arrows. It's a complex equation, which basically means that, in theory, yes, you can reach any number. Yeah, because that depends on P and Q. Wait, no, that depends on P and Q already being in the... Wait, if P and Q are in some omega, what that basically means is that based on the P and Q in some omega, you can reach any number. Well, basically... Wait, what? Confusion setting in. Aren't omegas defined only in relation to hyperoperation, don't you? Yeah, only to anti-hyper operations. That's how omegas are defined. Yeah. This is actually completely wrong. It should be M is contained. Me special characters. Characters. Oh, looks.
What if it bumped that control by accident? You'd be mincemeat by now. What have I told you?
All right, I guess I wasn't thinking.
You weren't thinking. You mean you'll work on engines and machinery and not think of your own personal safety? Here, shake hands with danger.
Wait, how do you use the... No, it's there it is. Great. This omega 1. This gives us some delta in between them, but that's not what I'm going for, is it? What I'm going for is this thing, except dependent on the n. It has to be dependent on the n, otherwise it's pointless. Unless it just is dependent on the n. What if it is just dependent on the n? What if we do this? Would it still hold true? That's the question. Because all this proves is that there is a number in between them, which never even was a question. For some delta, yes. Some delta. And now we just need to show that we can reach some delta using only the you can reach the delta wait, no, because that's any delta. That's wrong. That's wrong. I'm showing the wrong thing. What I have to do is I have to show that there is some delta you can get using... I have to basically show that there is some number you can get using hyperoperations n, and you cannot get it... that you can get using hyperoperations n plus something, but you cannot get this number using hyperoperations n. That's what you have to show. Okay, great. this in between P and Q, that's still will be decent, I think. Still will be helpful. Now we just have to show that we can reach. Wait, no, that's also wrong. Is it? No, maybe it's not. Ah, that's absolutely wrong. This is wrong. Any with any, not between which, but now let's pink you some omega, and that you cannot use them to create some delta using only n or smaller hyper operations and anti operations. But you can reach it using n+1 or higher hyper operations or anti hyper operations, anti hyper operations. Actually, they could be anti-operations because they are in relation to hyper-operations. Doesn't matter. Matters not. Okay, great. Cool. How do we do that now? Well, so glad you asked. You see, using the half function seems correct, like correct thing to do, right? Because basically the question we are asking, the really simple question to ask is that, can we reach the half? Oh, that's such a good idea. Okay. Now we can see why the half function would be useful. Yeah. It uses an n+1 down arrow.
He's a film distributor. He's at the front of the station. And Brown, he's filming
Arrow.
at the station. I know. You're trying to make me the ball guy. And Harris
So if we can, so if we cannot reach half of n of some number p, I suppose. Actually, half functions should have two operations. Later on we'll have also the, well, no, half functions should have only one, but p. Yeah. Cannot reach half of p. Half of p by only using.
all we got are suspects. My job, find out who.
The n will be really annoying here. N will be really annoying. Let's call this capital N. Using only n, n+1. So n is greater than n plus 1, only n is smaller than 1, smaller or equal to 1. Yes. And anti-operations, but you can reach it using n is greater or equal to n plus 1. Or n is greater than this and smaller than n plus 1. That seems cleaner. So we can reach by using only n operations. That means for any given n, there exists a number in some omega n greater than n, which is not reachable, but is not reachable with omega n. Great. Now how do we prove this? Well, that's a bit of a different story, but that is possible, because what that basically means, half function is unbelievably useful. What it tells us is amazing, because what half function tells us is half function p up arrow n up arrow this is equal to p, which means that this all uses n, right? Which basically, because this uses n plus 1 already. So that's convenient. This already uses n plus 1, which basically means this should be n. Yeah. This already uses n plus 1, which means that does squared away. So if we just prove that half of p is not in omega n, then we're done. You can reach it. So we can reach half waiting on the operation number for given n. There exists a number in some n is not reachable n. Yeah. So now the question is, can we reach? What would it mean for us to be able to reach to half operation of p? What would it mean for us? Well, it would be cool. It would be cool to finally understand something. What would it mean? It's page 11. Okay, well, I did write some stuff. May I remind you that it's only the half of these things that I wanted to do on this stream, and we're not even done. Alright. What would it mean for us to be able to reach half of p in relation to a hyperoperation? That would mean that the number q let's say now that we will attempt with proof by contradiction. Let's assume that that will be q. Not inside hard, but there we go. That will be q. If that would be q, that means q operated on itself with n. arrow, Q operated on itself with an N would be equal to P. Now we know what Q... Now we know what this is, right? Because thing operated on itself with an operation N is just one operation higher, the second. Is this any closer? Which would mean that Q with operation 1 higher would be equal to P. Any ideas in the chat? No? Okay. I'm dumb, I think. I feel like I'm really dumb at this point. Q hyper operated +1 and +1 on 2 is equal to P. What does that mean for us? Well, it means that Q is half of P in relation to N. We know that already. We know that. Also means that Q is equal to... Yeah, we can revert that now. We just proved the half again, which was not even the question. But we can, if we want to, we can, because we can just write it down like this. If in case we would like to. And we just proved that Q is reachable. Well, we went full circle, how neat. Great, I love that. I love that, we went full circle. What shall we do now? Wait, strings of happy operations, how will it look like? Whoa, that might be onto something. I know I might be onto something actually. X plus A times B. What does that mean? That means X plus A plus A plus A B times. That's what X plus A times B is. On the other hand, X times A to the B is X times A times A times A B times. Which means that hyperoperations, when applied in succession, give us the first operation applied third number times. How can we note that? What notation shall I use for this? Arrow hat? That feels cheap. Basically, I'm trying to introduce loops right now. Great. 6. I know that I like that idea of B times. It kind of destroys the generality. Yeah. Kind of breaks the generality of the situation. And even if we cannot really use that in that case, because what I was trying to achieve, right, is just basically Q to the N plus 1 like this, to the 2 to the n plus 2. Which basically means hyper-operating, almost multiplying, hyper-operating on both sides by p to n plus 1. No, hyper-operating, wait. It's operating, hyper-operating on n plus 1 p. No, n plus 2 p, yes. But you could do n plus 1 too. N plus... Wait. X plus a times a. Should be like this, by the way. Wait, do these distribute? That's a good question. X times a to the b. That would be x to the b times a to the b. These do distribute, right? Yeah. They can distribute on the operation one less than itself. That would mean that we could take this. They do distribute. I'm trying to achieve at least anything. Like this. Alright. Then we can do that. And we can operate it on n plus 2. Except we'll have to operate it on both sides. They are equal, so matters not. And now we can distribute this. Which means... What's really neat too... You know what is really neat about 2? Is that no matter to which operation you bring it, when it's 2, it will always be equal to 4. No matter which hyperoperation. That's what's really neat about 2. In case you do not believe me, the rise of the influencer. Oh come on, really? Try to bypass the system. No. Which means we could get up to 4. I did bicycles wrong, haven't I? Yeah. I did. Well. Very cool. I still don't think it gets us anywhere. I still think we're missing some variables here. But Desmond, listen, look at this. It's for me it's at least always fun. So first we have x plus 2. Wait. So x plus 2. We're studying. Yep. X times 2. X to the power of 2, x to the x, always 2 is a fixed point. It's amazing, it's amazing, it's just absolutely amazing, outstanding. And that is because of the fact that x to the x hyperoperated n x is equal to x hyperoperated n plus 1, 2. Which means that if x... I don't know where should I squish that thing, that fact. So let's just put it over here. X some, and by the way, this should be again. X is the is equal to now over here we'll need, yeah, this will be oh, element. Oh, great. Which means that 2 to n, 2 is equal to 2 n plus 1, 2. Which means that n, no matter which higher operation, right, n, it will always be equal to 2. Which means that this is kind of funny actually. And 2n is always equal to 4 for any n. That's really comical. For any n, it's always equal to 4. Because that's a fixed point, kind of, right? Which means if we go over here, we can replace this with a 4. This will be just a 4. Which means it's still a mess. It's still an absolute mess. An absolute circus. Wait, when did it change from n plus 1 to n plus 2? Whoa. Oh, because we distributed that. Yeah, so now n plus 1 to 4. Yeah. We could divide both sides by... not divide. Anti-operate 4. Yeah, I guess. Down arrow. Okay, now one last question. P, because that's... That's really upsetting. Yeah, we are in a bit of a pickle, aren't we? Because of this blood right here. Okay. Both of these have n plus 2 second, there's only this scaling down factor. n plus 1 fourth. Anti n plus 1 fourth. What happens if we bring something... Okay, we can check that. What happens if we bring something to... So, x... x up arrow... n up arrow second. Right, and then bring it down by 4. N. Let's first have the easier case, right? This one. Later on we'll get down to... Wait, can anti-operation 4 be expressed as anti-operation 2, anti-operation 2? Yes. I'm pretty certain. I think. Well, I mean, well, this also should be plus 1. which means that this would be equal to x to x, which gives us kind of nothing. Up by x, down by 4. Wait, but over here we can do up to +1 and p. I'm trying to get some kind of juicy contradiction. I mean, we have a really nice relation between p and 4 over here. A really nice one. By the way, q is supposed to be smaller than p, right? It has to be smaller than p. The delta here is absolutely useless. Which means that if q has to be smaller than p, I'm guessing, I'm guessing, it does it? It does not, does it? No. What's half of quarter in comparison to roots? What squared will give us a quarter? It will be a half, which means half is larger. So no, it does not have to be smaller. Because half of 0.25 is... half in comparison to multiplication of 0.25 is a half. 0.5, I mean. So, yeah, no. There's no... I'm looking for some juicy contradiction, as I said. Well, if p is equal to 4, then that would mean that... well, that would actually... if p would be equal to 4, then that would be actually really funny. It would be... that would mean that q... okay. If it works for any number, can I just input any number? Because right now it would break. It would just straight up break. If I input 4, right, then what I get is... 4 and n would be what? What operation would be n? No, I think p and q should... I mean, p should be in exclusively to delta n, right? Yeah, I'm not trying to generalize that. I should not just input 4 here. That seems a bit cheesy. If some more advanced mathematician than me would input 4 here, then I would trust them. But I am not a more advanced mathematician, so I don't trust myself. I mean, it's good. We have n plus 1 everywhere. It's convenient. We also changed it to this, which is absolutely crazy. N plus 1, the q. And the fact that the right side is 4. This is interesting, don't get me wrong, it's very interesting. We can replace P with Q. We can replace P with Q. Yes. My P's. My Q's. Yeah. Q. This is a P. This is a P. And let's change it to +1 because that would be just straight up way more convenient. So let me just change that so that this will be 2 + 1 and +1 2. There we go. That's just straight up way more convenient. And now we have everywhere we have operating on n+1. So how do we? Well... Or maybe we should leave it as... Wait. A times B times C is equal to just ABC. We can drop the brackets then, right? A plus B plus C is equal to... Can we? No, almost got me there. Order of operations, we cannot drop the brackets. Brackets are unbelievably important, they are unmovable. Do not move the brackets. But we got something very peculiar here, I would say. Q to the Q is equal to Q the second, and all down before. Ah. I guess we could also express this only in terms of peace, right? Let's try only in terms of peace. So, we have P this over here. Now, Q... How do we express this? Well, it's a half of P, which basically means this. It's this in terms of only P's. Also express this. I'm trying to express this in every single possible way and then check if something could work. So 2. Ah, that's so very upsetting. It's n+1, n+2. Ah! Grind to gears. I just feel like I want to input every single number here and check until it works. Every single number in the uncountable infinity. n+1, 4, down. Why? Why is this in brackets? It's so upsetting. So upsetting. So unbelievably upsetting. That is in brackets. Wait a second. Cannot we move this on the other side? You have to be very careful with the other operations here. Because this and this, it would be so perfect, wouldn't it? Actually, wait, these are both up. Wait, these are both up? And these are both down. I really hope I didn't make some mistakes. I really hope I did not. Okay, over here we just... What do we do here? What have we done here? Q second. What happened? Wait, what? That's wrong. This right here. That is just straight up wrong. Okay, time out with this. Let me just check this step by step. That is straight up wrong. This could be changed to +1 if you want. It could be changed to +1 of this. There we go. That's correct. We could anti-operate on both sides. But we have to be careful because then this is anti-operation plus 2.
Do you have a recent case? A case, say, in the last year or two that might be of interest public? The feature story along with the article. Something a little, with a lot of excitement. You know how it's are.
Well, this dance hall racket might interest you.
Dance hall racket.
Long story. If you've got the time, I can.
Well, I've got the time. Can I hear the story?
Helen, bring me in the dance hall racket.
If we anti-operate by n plus 2 to 2 on both sides, we just get back to this. Well, this actually. Pointless. I have no idea where this 2 come from. I just straight up messed up, so all of these calculations can go left themselves. It didn't work. Ay, caramba. Q can be... okay. Q can be expressed as P like this. In case you'd really like to. In this case, you know what? Screw it. I would like to express Q like this. It's like this. And then because of that, over here we have down to up to, which means we can drop them. That's just P at this point. Good old P. P operated with Q like this. Drop these two because they genuinely do not mean anything. No, I will not go mad. I can do it. It's fine. It's easy. It's easy math. Come on, make it. Kindergartners could do that. Some smart ones, I know. Right now all I have is just equality. Boring equality, no contradiction. Both sides are equal right now. They mean the exact same thing. Wait, that's Q. Wait. This is Q. And I guess they will have this very nice equality all the time. And that's because this is not what we are looking for. What we are trying to prove is that there is no way to express Q without using n plus 1. And, well, yeah, how am I supposed to prove that there's no way to express Q as with n plus 1? That's a good question. I'm so glad you asked. Absolutely no idea. I could ask ChatGPT for some example case. Not to solve this for me, obviously. ChatGPT wouldn't be able to solve that because it's too weird. I guess it would be the most appropriate way to. But I could ask him, considering numbers A and B, considering numbers A and B, where A is a rational number and B is a root. Could you prove to me that? How am I supposed to prove that B cannot be equal to? B is equal to root of A. Wait, B would be sometimes equal to. Whoa, whoa. Okay, so B. When it goes to the root thing, right? The rational numbers, B would sometimes be in the omega. So now the question is when? Well, it would be in the omega.
We all enjoy being together, but is anyone left out? Think so. Well, that's our guest list. Now, invitations. Should we write? Dear Alice, would you like to come to a party
let's consider that. Wait, that totally, Q totally could be in the omega n, capital N obviously. Q totally could be the omega n. If P is some number which hyperoperate, if P is equal to well, P is equal to Q hyperoperated n plus 1 itself, that's obvious. Another hard. No, this is not an easy problem to solve.
We have to feed the men and the girls too, especially you. Gee, thanks. The show. Well, we want something to eat, something to drink, refreshments.
Alright, no, yes. I already drank half my coffee. Wait. I know I keep saying wait, it's boring, but I still am thinking about the roots and powers. So basically, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. Over here we have 1, 2, I know I said in the middle, 3 numbers, which basically have this property that half of the number gives us something that's contained in omega, right? So basically 3 numbers over here have property. Let's focus on numbers that don't have this property, like 3, 6, or 8. What do they all have in common? Well, these numbers all have in common. Actually, I'm focusing on the wrong thing over here. It should be... it should be rather even numbers, actually. yeah, we're working integers, should be even numbers. Focus on even numbers, because that's the integer version of puffs.
Sure was, but I never heard it played that way before. Well, a good tune can be done anyway. Now, wait a minute. Hold it, lads, wait a minute. Wait just a minute. Show Johnny, we'll prove it. What do you mean, play another tip? Johnson, no. Johnson, right, as a waltz. As a waltz, you got it? Here it is.
Wait. So for some number p, right, is equal to half of n p times the 7, right, yeah. But now, so those numbers exist. They will always exist. They will always exist because always all you have to do say that this one interesting thing to mention is the fact that numbers whose halves are contained in the appropriate omega n will always exist, because if there is a number I should really copy something that's shorter like this. If there's number b, which is in omega n, then b up arrow. Wait, I did copy up arrow, didn't I? Okay, great. N plus 1 up arrow will be equal to sum a, and a will then be contained within, then a will be will it be now? What's the proof? Where's the proof for that, make it? You have to prove stuff like this. Why would A be there? It would be there because, first of all, B over here. It would be there because the definition of stuff running out of omegas depends only on down arrows, only on anti-operations. That's not a proof. That's very much not a proof. Okay. And, I just have to open. Oh, quite a while. So, well, my office, my room is actually well ventilated. My office isn't. Okay. I mean, it just will be. It would have to be, because then you can describe the number. All these uses are a description for O. You can use this O thing. Because yes, we can use this one. Except we'll have to make this even smaller, because oh my goodness, it will not fit. That's what she said. Just kidding. Oh, come on.
Got it just about all planned. I thought we'd finish off the evening with a little dancing.
Dance? I hope they don't pull that stuff at our party.
What are you worried about? You can't dance anyway.
You can, I suppose.
That did not work at all. Okay, so this, if we up arrow that, right? Because this basically gives us an equation for any number inside the omega n, which means if we up arrow it n plus 1 by itself,
What do you got there, dear?
Oh, just some stuff for Halloween.
up arrow,
I'm the treasurer.
Oh, I didn't know you were gonna have a Halloween party at school.
Well, we're just gonna dress up and play some games.
Oh, that sounds like fun. School parties always are. You better. We get out of study.
Yeah, Halloween's a lot of fun for kids.
you have this is n. The highest one is n. The highest one is n. I need at least n plus 1 for this to work. Well, do I? Not quite. I actually do not. Up arrow n plus 1. I will need a lot of space for this to work, but I will not need. Where the highest anti-operation is still equal. N.
Wait a minute, where are we going? Oh, to the party.
Cool. Which means now all we care about is... So now let's say that P and Q both are such numbers, so that half of P fine, is in omega n, and same thing except for P. And can we say that these are the two smallest numbers next to each other? Most numbers such that they did this. Can we say that? Well, not quite, can we? No, maybe we can. No, we cannot. Can we? We cannot. Can we? We cannot. Ah, fudge, the freaking uncountable infinities are so annoying. Am I right? Oh wait, can we not just have it forever? Like half and half and half and half and half? Can we not do that? I mean, at some point we would have to reach. The problem is that when it comes to roots, right? When it comes to roots, we have to think about rational numbers, which means that these would have to be two rational numbers, so that rooted, they will give you other rational number. Numbers which exist, I mean 25 16th, right? That would be, I guess, one of them. Problem is, can we have two numbers that would be in between? Ay, caramba, it's not an easy dilemma. Let's say that P. Now let's say that this. Yeah, now let's say that half of P is actually in there. Should be should be capital N. Actually, no, because we are generalizing, right? No, we are doing it for some. Yeah. So I'm kind of bit of ideas here, because those numbers do exist, and what I have to prove basically is that if you have a half forever, if you have halves forever, then at some point you will reach a number which would have to be some different. Okay, I guess I could prove that without. Wait, half of. Oh, I got it. Okay. Okay, I got it. Okay, get it. Cool. Sick, amazing. From a country? No, just. So now we have two possibilities. Or is not contained because it can be this. If it is the possibility number 2, I wanted to do a sophisticated way. No, just simple way works. Possibility number 2, then congratulations. E of requires a different omega. If it is the possibility number 1, then we can just repeat the process. Which basically means that here all we have to do is just this and this. Or this. And then repeat. And so on, until we reach a point Q, reach number Q, number that is not in omega n. Great. So now we just proved that number. Great. So now we just prove that every next omega has more numbers than the previous one. Now it is time to show that for any number, what would be the most delta? Delta, there exists an omega n that contains it. How? I have absolutely no idea at this point. Not gonna lie, I have absolutely no idea how to show that. For every omega. Well, yeah, I have absolutely no idea how to show that. For now, we'll have to be anti-operations cascade so that. possibilities if b is not equal to 0, 1. Great. So I still think that this is kind of funny. To any hyper. Okay, great. So now, this is the way more important bit, way harder to prove. That was just the warm-up. That was all just the warm-up for this. Okay, how do we prove that now? Well, good question. Ah, great. Good question, you know, how do we prove that? How do we prove that? How do we prove that? For any number delta, there is an omega and that contains it. Well, what that basically means is that there is a finite... Well, here's the thing. The way I wanted to do it is... like, take an omega... like, start with omegas, and then based on that, prove that there is a finite expression for any number. Finite expression for delta. That's the top 10 deltas. There we go. Great. But I think we should do that the other way. We should first prove that there is a final expression for delta, and then we'll be able to prove that it is contained in omegas, which then would mean that... So we'll have to prove that there is a finite expression for any number using only hyperoperations, which is, well, let's just say, bonkers. But, I have no idea how to do that. Contains it. I would love to just add one more thing, which is header 4, new operation. There is only one operation we are missing, and that is because in conventional mathematics it is not used that often in relation to multiplication and addition, and those are logarithms. Yes, good old logarithms, because here's the thing. They would complete our triangle group of equations, so that A up arrow n up arrow B is equal to C, which means if we anti-operate both sides, what we get is the same thing except down arrow and B. And now, what happens if we want to get B? Well, if we want to get B, what we obviously do is we take the logarithm. So if we have a to the power b is equal to c, what we do is we basically take logarithm base a. So b is equal to logarithm base a, which gives you c. What kind of equation can we do for that? Well, latex arrows. What kind of arrows do we have here? Up down is really tempting, but I think right arrow That seems like the right thing here. Right arrow would suggest though that there would be also left arrow, so maybe up down arrow. That seems. Yeah, there we go. And funny story, this is actually would be correct for every single equation, which means that this should be, by the way, the other way. I just simply cannot look at it this way. C is equal to this, and then you know this should be over here. Oh, I like, look at that. Oh, it's beautiful. Okay, great. And we have a recombination. Well, we have a way to get A, we have a way to get B, we have a way to get C. It's great. So what now? Well, actually, we do not have anything. We could... Wait. Could switch these around. B and C. C to the B and B. Now the reason why what should we call logarithms for every generalized? We have hyper operations, we have anti operations, and we will have operation. I need some third name for this. Operation, no. Hyper operations with an I don't know. Hyper prefix. Wikipedia. Hypertext, what would be the antonym? Antonym for hyper. Hypo. Hypo operation. Why hypo operations? Hypo operations not used that often in conventional mathematics. Is because addition and multiplication on the real numbers are commutative. So A is equal to C plus B. Just like that. So when A is equal to B plus C, then B is equal to A minus C, and C is equal to A minus B. But the B equation is obscuring the truth. It works only based on yeah. If it was not commutative, then you would not be able to get a B there. Only is very dramatic. Let me just it's only based on commutativity. Now, considering that in the hyper operational world there is no convivity, we have to define hypo operations as something different for any n. I wonder how many mistakes I've made because we were lacking hypo operations. Hypo operations. That's a good question. I hope none. Did we do any serious calculation? We did not. That's good. That's very good. That's very good. Now all we need. Now we have 3 tools basically. I have to rewrite that. A is equal to... Yeah, I have to rewrite that, I'm sorry. This should be over here. Alright, so A is equal to B to the power C. Then B is equal then to A to which power C, yes, and then C. No wait, that would be C, yeah, because B then... Oh, just leave it as it was, boring but fine. Yeah, A is equal to C. Let me check. It works. A is equal to... B is equal to log A C, and then C is equal to A to the power B. Yeah, so if we take root of both sides, we get A, and log... Yeah, okay, cool. Hypo operations are really often missed, because our math is mostly commutative, except for exponents, which are not commutative, and that breaks the thing. As I said, multiplication is also commutative only on real numbers, which means that if you were calculating quaternions, only on complex numbers actually. On complex numbers. So if you were working on quaternions, then you would be screwed up. Just that. So, can we prove now that for any number delta there exists an omega that contains it? Good question. How do we say, how do we even express mathematically any number? Any number. Any number. Any real number in the world. Any number. It's a fun thing to think about, but no. Well, I guess I'll have a think about that, and I'll end today's lesson for now. With a lot. I mean, we're on the 12th page. One day maybe we'll have like 100, that would be fun, because that means that there will be something interesting here. For now there is, if we prove that omegas contain every single number, then we have this, which is a rather fun equation. This is basically an equation for everything. This equation could describe any number if you have the n, which is fun. Which is a fun idea. Alright, well, I guess on the next lesson we'll try to prove this. But that'll be it. Thank you all so much for watching, and have a great day.